Now we welcome Rebecca Glarin. Rebecca is the lead research radiographer at the Melbourne Brain Centre's imaging unit at Melbourne Uni. She has over 20 years experience in both clinic and research MRI, with almost 10 years working in research as 70 ultra-high field scanner. Rebecca's research interests including functional MRI and spectroscopy, and she's currently completing a PhD in functional brainstem imaging and the focus of autonomic physiology. Let's welcome Rebecca.
Hi, so I'm actually, coming at this from a bit of a different perspective. So I'm coming at it from, I'm going to help you make the sequence and set up the neurofeedback on your scanner. So I think it's important if you're going to start doing neurofeedback that you have that relationship with the vendors to help you and with the software companies, as well as the people that are building your sequences for the scanner. I'm not going to go into too much detail, it's not a physics lesson. But it's just the things that you might consider. You can't just walk in with a normal functional sequence that you've run in normal cognitive studies and say, I'd like to apply this to real-time feedback. It won't work like that. I'll go through in two sections. First of all, the parameters of the EPI sequence. And most of this is in relation to your signal that you'll be needing for the real-time. Yes, you need to consider these in your post-processing, but it's how it applies to be able to use real-time feedback. And then I'll talk a bit about setting up the data transfer. So for those who, I don't know who isn't familiar with fMRI, but it uses the contrast of BOLD, so blood oxygenated level dependent imaging. And this focuses on the diamagnetic properties and the paramagnetic properties of the haemoglobin with and without oxygen. So you can see here in a stimulus of rest, stimulus, rest, stimulus. In the resting, the concentration seems to be quite spread, but as you invoke a stimulus, you change the local ratio of the oxygenated to deoxygenated blood. And this causes a change in the magnetic susceptibilities of the signal, which then produces a change in the T2 or the T2 star. Now, we're really lucky at ultra-high field that the T2 star is more prevalent, and we are able to use this to exploit better signal in our imaging. So if we move on to signal to noise, which is really what it's all about, you need enough signal in your ROI to be able to produce the neurofeedback at the time. So for us at ultra high field, this became a bit of a challenge because you can push things further and further in terms of your spatial and temporal resolution, but you don't want to push it too far for what you want in your post-processing, and you want that higher resolution that you're not getting the signal you need in your real-time raw data. So just a little thing here, we know that as the voxel volume increases, SNR increases. And as field strength increases, this is even more obvious. So 1.5, 3 and 7 Tesla. And this is across all image weightings. This is not necessarily for BOLD. But if we look to BOLD, we can see here as we invoke a stimulus, back down, stimulus, rest. One stimulus in particular, 7 Ts all the way up here compared to 3 and 1.5. So you can see these gains that you can get in your signal to noise and contrast to noise in your BOLD imaging when you move to ultra high field. So can we exploit that? Yes, we can, and we have. As Chow mentioned earlier, some sites are using, for their 3 tests, they're using like a 2.5 millisecond TR. We're using a 1 second, even an 800 millisecond. So with that, the high SNR is essential, but it comes with some considerations. It's this trade-off again of what you want to get out of your post-processing data compared to what you need real-time. There is no ability to sample the same paradigm over and over and over again and combine it in the post-processing space if you don't have enough signal to be getting any activation in your ROI. So you can do normal post-processing of of noise regression using something like Nordic in the post-processing space, but again, you can't do that real time. And also to consider when you're designing your paradigm, that participants will fatigue. I think this was mentioned earlier as well. So you need a robust enough protocol or paradigm that participants can perform it for 10, 15 minutes and produce that feedback that is going to get you post-processing results you need, but also enough activation real time again. So these are really important considerations. So if you move to the repetition time, so this is the time between 2 successive radiofrequency pulses applied to the same slice of tissue. This is a study by you. This was performed on our scanner, right when we were getting to know it and understanding how we can push the scanner. And you can see here that with different spatial resolutions and 3 different temporal resolutions, actually it's looking like the signal is quite similar. So it's showing that there is this range, it seems to be, between your TR that's still providing enough signal that you're going to be able to use this in a real-time perspective. And so if we look at that closer, there's statistical comparisons, and this shows that even though it's statistically higher temporal resolution seems to improve the bold contrast, the effect is quite small. So this again supports that window. So it's important to get to know your scanner and understand where you can push that TR range and still have enough signal to noise and contrast to noise. And also, if we talk about repetition time, we also have to talk about the echo time, and that's the time between the radiofrequency pulse and the time we receive the signal echo. And so this is a schematic here of considerations. So the oxygenated blood and the deoxygenated blood, and you can see as you move through time, actually the difference between them is quite similar. So it shows you that there's actually a range that you can pick your TE that it will still provide significant contrast between those 2 susceptibilities in the bold imaging. At 7 Tesla, it's about 30 milliseconds, but actually you want to kind of push that as far as you can down to maybe potentially 20 milliseconds, because this is going to allow you more flexibility with your TR, and you can essentially get a shorter TR, which is going to improve your temporal resolution. Now, we wouldn't use multi-echo fMRI or MRI for neurofeedback, but there's just an example to show that you're getting this stronger contrast to noise in that first echo. So if you're wondering, maybe I should be trying a later echo, the signal just isn't there, and it supports this, as we see over here, to be shortening it's okay to shorten that TE. Phase encode direction. Now, this might not be something everyone's kind of aware of, because normally you can acquire your fMRI data, your EPI sequence, and then you can acquire it in one phase, acquire a reverse phase, and then correct it in something like top-up. But because you're getting this real time, you need to be aware of the distortions that are caused by your phase direction, so AP or PA. Now, I'm going to attempt to flick backwards and forwards through these, but I'm not always good with this mouse. But this is phased in the PA direction, so posterior to anterior. These are 2 different heads, 2 different scanners, 2 different spatial resolutions, one smoothed, one isn't, just to show you that this effect is across all different types of imaging sequence. So you can see here when you reverse the phase and phase from the anterior to the posterior direction, I knew that would happen. There we go. So, and the head on the left, it's not as obvious. But on the head on the right, there's a dramatic, I'm going to do that 50 times. There's a dramatic stretching in that midbrain structure and that frontal lobe. So if you want to consider, if you're always anywhere near a region that is near an air tissue interface where you're more likely to get those susceptibility artefacts, that can potentially cause a lot of distortion of your signal. This can be corrected with the alignment in something like Turbo Brain Voyager, but the more processes you put into the data that you're sending to the Turbo Brain Voyager, the longer it's going to take to process this. And this is part of what I think a lot of people have mentioned that you get in these delays. So the more robust your raw data is that comes off the scanner, the less chance that it's going to cause delays in the post-processing. So the phase encoding can cause a few artefacts. There's some other reasons to consider. Blood flow, motion and acceleration. So some solutions would be pick a region that's not sitting next to a highly vascularised area. For your motion, the Turbo Range Voyager and the other softwares can motion correct, but this also adds time. So you want to make sure your person's securely in the magnet and try not to move as much as they can. But it's also a reason to, when you're piloting, test and test again. Because you're putting each other in and you're like, I need this data to be perfect. Like, this is my PhD, this is really important. And then you put a normal member of the public in and they've moved all over the place. It takes longer to process, and then you've hit a delay and then everything times out and it fails. So these are the sorts of reasons with your buoy placement and your sequence choice that you need to test and test again. And the same for the acceleration factors. So now we can push things with our multi-band, our simultaneous multi-slice, our grappa artefacts. But with that comes, there's often a calibration scan at the start of each sequence for 30 seconds. If the participant moves in that, you'll then have a ghosting artefact across all your images throughout the acquisition. So you need to QA at the time, make sure you don't have an artefact where your ROI would be, or consider reducing those acceleration times to reduce your chance of an obvious artefact. And with that will slow down your temporal resolution, which will also make your reconstructions a bit faster and can help reduce delays as well. So that's it for the imaging side. Hopefully the people you work with can work with that with you. You can say, I've heard about this, heard about that. But then we move on to the data transfer. Now, this was set up with Sampras and someone else in our lab. I'm not going to go into too much detail because a lot of it has kind of been gone over today. But we've got our scanner console, our presentation computer, and our Turbo Brain Voyager computer. It is vital that you need to connect all three of these to each other. And if they are not connected, or you think they're connected but you haven't logged into each of them, they fail. And then once you have this connection set up, you need to get your scanner to commence simultaneous sending of your DICOM data. So when the data is acquired, it sends immediately to the Turbo Brain Voyager. Now, if you're scanning on a 3 Tesla or you've got a longer TR, you have more time to do this. The delays may not be so prevalent, but pushing it at ultra high field, it is really important that this send is efficient and that it is very simultaneous and there's no delays in that process. Then, once you know how long it takes to send your data backwards and forwards, you can then design your paradigm now that you know those restrictions. Then when you've designed your paradigm, you can then choose your sequence parameters accordingly. So an example of this is, we have one study that we ran at 800 milliseconds, but the feedback was given at a block at the end of each section. So if there was a slight delay and one took 900 milliseconds to get there, that was okay because it would catch up by the time the presentation happened. But if you're providing real-time feedback, so every second you're acquiring, it's taking a second to reconstruct, it's sending over, you need that to be as accurate and as timely as you can. So you may actually want to build a buffer, and that's what we did. We turned our 800 millisecond into a 1 second TR so that we had that buffer if there was that tiny delay that it wouldn't crash the system. And so it seems, I don't know if we've emphasised enough, this process takes a long time to set up. So once you've set it up, you test it, and then you test it, and then you test it again. And even when you've done that, you'll think you're ready to go, and it'll fail again. And then you'll think you're ready to go, and then you do another pilot. But that's okay, because once it's all, eventually after a couple of years, you end up with a robust system. So our considerations for our data transfer were the security of our network. So connecting anything directly to our scanner, we need to make sure that this is safe. So we put our Turbo Brain Voyager and our scanner on the same VLAN. And we made our Turbo Brain Voyager a solitary computer that we control our software installations on, and it only connects to the scanner and to the presentation computer. And then at the start of every session, this is on our scanner console, we unlock our Turbo Brain Voyager share drive, and we unlock it on our Turbo Brain Voyager and on our functional computer. So once you've unlocked that and you've got your network and your connections working, we have to set up our DICOM transfer. So this needs to be done every time we open the participant. So if you're fiddling around, you may find that your connection is lost. So you need to open your participant. I don't know, sorry, you can't see that from here. I can't see it either, but you go into this is Siemens, into the IDEA command tool. It's telling you that it will close after each participant. This is setting the network drive to the Turbo Brain Voyager. Then turning on the switches that you want to send something. And the last one is that you want to send your images. So it's actually, it probably looks more complex than it is, but it's a couple of 5s and Qs and bits and pieces, and then that's set that it will automatically send every image that is acquired directly to the Turbo Brain Voyager. But something that's important to consider with that is if you are modifying your paradigm, if you want to add in distortion correction or you want to collect your phase data as well, as Amir mentioned, you need to consider the number of your DICOM, and because you've got this automatic transfer on, the minute you change something on the scanner, you might collect physio logs or something, it will change the numbers of your sequences, and that will then change the number of the DICOM that you want to be receiving. So just be aware that once you switch this on, it's sending everything, and it can potentially mess some things up. And just a bit about the transfer delays. So they're not consistent, and they can limit your parameter choice. So as I mentioned before, we put a buffer in to help with this inconsistency in the delays. And if you really want to push it, I mean, as Sampras mentioned, there are some people that are pushing it. You can pipe your reconstruction, your data straight from your image reconstructor on your scanner to your Turbo Brain Voyager, and don't go back into the scanner system and then back out to the Turbo Brain Voyager. So that's an option. And with that, I should have said with your computer, try and get it set up for exactly what your software version suggests. So the same CPU, the same GPU, that sort of thing. And that will help with the potential delays. And also changing the size of your ROI. I don't know if anyone's mentioned that, but the bigger your ROI, the longer your calculation will take. So if you're finding noticeable delays, you can consider altering that, or you could lower your spatial resolution and have the same size ROI. So there's ways you can move around that. So in summary, test often during your study design and your piloting. Can't emphasise that enough. Create a really robust data transfer efficiency setup that suits your needs. What we've presented today might not be what you need for your scanner, but take your time to have it how you need it. Consider the speed of your transfer and the delays on the reconstruction and the processing side, and take the capabilities of your system you've created into consideration when designing your paradigm and your parameters. So just quickly, thanks to my group at the NBCIU, thanks to Brad and Sampras, who spent a lot of time setting up this system on the 7T, and thanks to the neurofeedback team from ACU.